All right, hello everyone. If I could remind everybody to turn off their phones or at least put them on silent, that would be a good start. Hello, and welcome to Replay Technology in Overwatch, Kill Cam, Play the Game, and Highlights. I'm Phil Orwig, an engineer on the server team for Overwatch. And with that, we'll dive in. Overwatch is Blizzard's inaugural foray into the field of first-person shooters. It's a team-based, multiplayer competitive game featuring heroes with unique, over-the-top abilities. This talk will cover the design goals of our replay system, diving into the architecture and implementation details necessary to hit a highly polished feature. On the way, we'll cover some of the challenges and trade-offs we made, and we'll touch on some of the future goals around the replay system. What were the high-level design goals for the replay system? Well, the title of the talk might suggest an answer, right? At a high level, the requirement was that we create a single, central system capable of supporting kill cams, a play of the game, highlights, and in addition to that, we really wanted to have some replay files usable on the floor internally during development. Let's briefly dive into each of these features. Each time a player dies, Overwatch shows the dearly deceased player a kill cam, a brief recreation of the seconds leading up to and including their death, typically staged from the killer's perspective. The kill cam can help a player to understand how and why they died, and hopefully provides a teaching moment. In this sample video, you'll see the various beats of the death experience. You'll see the player die. There will be 3 immediate things that happen with that. We ragdoll your corpse, provide a toast of how you were eliminated, focus the camera to track your killer, and there'll be an outline around the killer in order for you to kind of follow them through walls and see what actually happened. We'll fade into the kill cam and provide a little bit of pre-roll context ahead of your death, a few seconds of post-death context. You can see your ragdoll and hopefully understand why you died. Now, while we hope that the kill cam is helping you learn and improve, not all players enjoy watching themselves die. I can personally attest to the fatigue that occurs when you're watching your hero repeatedly make the grand egress. When you're iterating on a feature like this, you start to develop a macabre sense of humor. Play of the game, on the other hand, is a rallying point at the end of the match, celebrating a game-making moment by you and your fellow players. It's a hopefully awesome moment that everyone shares at the end of the match. It inspires players to strive, improve, in the hopes of earning the play of the game, showing off the personalized touches they've selected for their hero. We're going to take a look at the end of round flow here, and we're going to go from the victory lineup of the winning team to a player-selected highlight introduction animation, transitioning into a hopefully super cool moment of teamwork and prowess. Oh. Technical malfunction, one moment, please. Yes, that was me saying GG to bots.
Play of the game.
They did not see that coming. No, I'm not really that good. Those were bots. So when players believe that they're going to get the play of the game, they tend to start showboating a bit, leading in moments like this. So here you're going to have a Reaper caught in a graviton surge that uses Wraith form to escape. That's happening right there. His ultimate meter is 100%. He turns around, drops a confident spray, and then pulls off his ult, completely clearing everything out of the way. The most notable thing about this, I think, is the fact that the player was so confident that they dropped that well-played spray ahead of the move. They were just like, no, I got this. Plays of the game lead to some pretty good storytelling moments, but what happens if you don't personally get the play of the game? Or if you got the play of the game but didn't have your capture software running? Our solution to that is highlights. While only one player in a 12-player match will get a play of the game, almost everyone in the match will receive a personal highlight reel, which is viewable from the lobby. This feature makes it easier for players to capture cool moments and share them with their friends. As an example, this highlight doesn't show off personal prowess as much as it tells a funny story. In this case, you're going to see a roadhog hook more than they planned on. I apologize, I don't think I have audio on this one. Oh, Alt goes up. Oh. Oh, bad. Oh. Oh. Party foul. All right. While replays haven't made it into the players' hands yet, they've been available internally for the majority of Overwatch's development cycle. We have a hotkey internally that dumps the last 30 seconds of replay data to disk. If the machine has some kind of DVR functionality like Shadow Play or what have you, it will also dump a video. As you can imagine, the combination of these two artifacts help us really isolate and fix a bevy of bugs that would have been much more difficult to recreate without a replay. Beyond that, replays have provided us a great way to repeatedly test performance over time. Developers can tweak code, measure the performance impact, and iterate, all without having to get 11 of their closest friends together for another playtest. Mind you, that's not actually hard on the floor. We just say, hey, playtest, and then there's usually more than 11 people that join in. But that's a productivity problem. Let's not do that all the time. During development, we also had the ability to ship a replay with a client that was specially built to first-party vendors to help isolate driver bugs and performance problems on particular platforms. So without further ado, we're going to launch from there into network synchronization, kind of the common models and how they interact with the design of a replay system. Your replay system will inevitably be tied to the simulation and network modeling for your game. Glenn Fiedler, in an excellent series of blog posts covering network replication, broadly categorizes synchronization mechanisms into three major categories. There's deterministic lockstep. This mechanism is commonly used in racing games and RTSs like StarCraft and StarCraft 2. Snapshot interpolation, which is a venerable model from the FPSs and is used in Quake and many FPSs beyond that. And state synchronization, which is a kind of refinement on snapshot interpolation. And that's what Overwatch uses. Please note I've included some resources that were inspirational for us when we were designing our own synchronization strategy here. Now for a whirlwind tour of these techniques. All right, first up, deterministic lockstep. Here we've got 4 clients, there on the left, connected to a server. That server might be another client pulling double duty as a server at the same time, but for the sake of this particular exercise, we can imagine a nice dedicated server sitting somewhere in a happy little cloud. The clients take their input and send it up to the server. The server locks the simulation until it receives inputs from all the clients, and when all the inputs have arrived, the server can safely step the simulation. With all the client inputs safely accumulated, the server batches everything back out and reflects it to the clients. Then the clients take that input and step their simulation based on the data they've received from the server. If you've done your job well as an engineer here, everyone arrives at the same result, and your simulation goes on its merry way. Building a replay system from this is pretty straightforward. You just record the entire stream, and you can play it back. You're good to go. It's also very small because inputs are usually very, very compressible. Deterministic lockstep simulation is architecturally simple, but there are some pitfalls associated with it. The simulation model requires strict determinism. Given the same set of input, every client must arrive at the same output at each step. If they don't, clients can desynchronize, disagreeing about the state of their simulated reality. Even something seemingly sane, like relying on deterministic floating point output, can be difficult to get right, especially across heterogeneous hardware. All it takes is an errant printer driver changing your floating point precision settings during an interrupt handler to throw you off the rails. And yes, that does actually happen. Beyond the engineering effort behind maintaining a deterministic simulation, lockstep simulation presents another problem for network multiplayer games. Waiting for all client input implies that a single stalling user can disrupt your timely simulation. This risk scales with the number of users in your game. Doing the math, if each user has a 2% chance of stalling out in a 5-minute time period, a game with 4 users has an almost 8% likelihood of stalling. When you're up to 12 users, you're at almost 22%. I didn't actually make a graph, I probably should have, but these pitfalls are, of course, surmountable. With proper engineering discipline, you can develop and maintain a deterministic simulation. Many games have done it, it's totally doable. With some cleverness, it's also possible to hide the simulation stalls due to missing client inputs. You can perhaps rewind and reapply the simulation or predict within some window on your systems. Ultimately, Overwatch opted against deterministic lockstep simulation for a few reasons. First, we didn't want to burden our engineers and designers with worrying about accidentally introducing some non-determinism. Beyond that, implementing join in progress on top of the synchronization pattern is non-trivial if your simulation is already costly. You'd have to basically replay inputs from the start of time. So 5 minutes into a match, that can be a lot of simulation. Implementing a kill cam can also be difficult. It would require some kind of client-side snapshot and roll forward mechanism. Of course, such a mechanism might already be necessary if you're building a game that requires save file support, but Overwatch does not. So what's the next option? Snapshot synchronization. Similar to the deterministic lockstep model, clients take their input, send it up to the server. The server here, however, can continue to simulate even in the absence of input from a single user. Instead of gathering and reflecting inputs back to the clients, the server simulates the world and generates a snapshot of the complete instantaneous world state. Then the server sends that snapshot back to the clients, which update their world state with new server authoritative state, typically with some kind of interpolation occurring between the two snapshots to smooth things out. This approach works well. It's conceptually simple, and it avoids both the determinism and stalling issues with the deterministic lockstep model. Add in some interframe diffing and some compression, you've got a really reliable model, in fact. While the diffing process can be expensive, you can typically only need to do it once, and you can amortize the cost of doing that snapshot or delta compression across the number of clients you're going to be sending it to. Unless, of course, you're worried about cheaters. In that case, you'll need a mechanism to elide data about units in areas of the world that a client isn't supposed to see, and so you're kind of trying to ride that line in terms of what's actually visible for each client. Building a replay system on this is also fairly straightforward. You start with a full snapshot of the world state. You append in the differential updates on each frame. This mechanism, broadly speaking, is how client demo file recording works for many of the games relying on the id-tech lineage of engines. The client simply serializes their network gameplay stream to disk. It's also conceptually simple to implement a kill cam with this architecture. You've got full snapshots, right? So you just maintain a ring buffer of world history, and you can basically snapshot back to the place where you were at and then just play it on forward again. Notice here that I've varied the size of some of the snapshots. You can imagine that the size of each frame here is a proxy for the serialized size of the snapshot. Some frames have less changing, and thus will be smaller. In this case, though, you can see I've also varied the pipe size. And snapshot sizes are kind of the Achilles heel of snapshot synchronization. It places limits on the size of your world state or the amount you can change on a single frame within your world state. The more things you're synchronizing, the larger the initial snapshot size. The more things that change frame over frame, the larger your delta sizes. More changes means more bits, and bits on consumer broadband connections are actually still pretty precious. Eventually, with a rich interactive world, if you want your game to work well with a low bandwidth connection, you're left with the last of the major categories of synchronization patterns. State-based synchronization. This is the exact same slide we've had for 2 points now, so same previous model, clients send up inputs to the server, which then steps simulation. In contrast with the snapshot synchronization model, the server doesn't attempt to generate a single update for all clients. Instead, each player receives a bespoke network stream handcrafted from the finest fair trade organic bits. What do we mean, though, when we talk about world state? Well, we mean whatever state is necessary to represent our world. You can imagine a ledger of individual translations, rotations, health values, animation parameters, weapon volley states, and so on and so on. In the snapshot synchronization model, you receive all of this data and apply it once atomically. State-based serialization breaks that world snapshot down into smaller atomically replicated chunks. Because each client is receiving a custom stream, we can prioritize updates based on what's relevant for the client or elide information that the client shouldn't know about. This allows us to intelligently adapt our gameplay stream based on the bandwidth that we measure on the client. In this example, we have one client that's receiving an update about both Reinhardt and Pharah in a single packet. The second client is receiving an update about Reinhardt in one packet and another about that same Pharah on a later packet. The important thing here is that objects can be updated independently from each other and that each client's network stream has been customized. While this model tends to be most flexible in the face of myriad quality levels on consumer broadband, it does tend to be more complicated to implement. This, again, is what Overwatch implements. Let's dive in now on how we manage that stateful replication in Overwatch and how the replay system meshes with this network replication paradigm. Overwatch uses an ECS architecture. So we have entities made up of components that are updated by systems. Some systems are what we call serialization participants. They are responsible for synchronizing some aspect of the game to receivers or replication targets. A receiver or replication target is something like a player or a spectator. There's somebody who's receiving data. That's hence receiver. Finally, A replication target is receiving updates about other entities. In a sentence, when I usually try to describe this, it's participants fill packets for receivers about network relevant entities, or what we call subjects. As a brief shout out to my fellow Overwatch developers, if you're curious about the other aspects of our gameplay architecture, network scripting, and netcode in general, there were additional sessions by Tim Ford and Dan Reed that fill over areas that I'm glossing over. They've already happened, so you can check them out on the GDC Vault. Okay, so let's try to put this in more concrete terms. Say you're controlling Pharah, one of the heroes in Overwatch. You jump, you fly, maybe strafe around a bit. How is this information reflected to players? As you mash buttons merrily along, your client simulates the predicted change, then sends your command stream for those changes up to the server. The server takes that input, along with the input of everybody else, and steps the official server-sanctioned simulation. Some entities move, some heroes fall, some projectiles get fired. It's kind of like a party. It's all great. Ultimately, each one of these changes and events is what we call a delta. So that change in position is a delta that has occurred on the server. So what we do is we accumulate all of the server-side subject state changes into a temporary per-frame dirty set. So you can imagine this is simply a set, literally a set in the mathematical sense, of the entity IDs of everything that changed on that particular tick. So how do we reflect that state back to the clients? Well, we maintain a dirty set for each connected client as well. So at the top of the slide here on the right, you've got the frame dirty state. That's the set of things that were dirtied on just this simulation tick. And at the end of the frame, each receiver's dirty set is unioned, again in the mathematical sense, with the frame dirty state. This tracks the exact set of entities that need to be visited during packet population for each client. At the end of the frame, after all of this kind of accumulation has happened, all the propagations occurred, the frame dirty state is emptied, and the whole thing starts over again on the next tick. At some point in the future, usually just later on that same tick, that dirty state will then be serialized out into a packet and sent over the metaphorical wire, there's a lot of wireless nowadays after all, to the receiving client. Once that data has been serialized, it's removed from the receiver's dirty state set. Bandwidth is at a premium, so rather than copying out raw state data into a packet, we maintain historical information on the server of the state that the client has previously acknowledged. We can then use delta encoding in order to improve the bandwidth model that we're dealing with here, and generally just reduce our bandwidth footprint. For the majority of frames, we have sufficient bandwidth to serialize absolutely everything. If we don't, though, it's totally fine. In this example, we serialized out an update for Pharah on this frame, but Reinhardt didn't fit into that client's bandwidth allotment on that packet. The receiver's dirty state will just accumulate whatever's happened, and then we'll eventually serialize that out in a future packet. This is one of the great features of the state-based replication model. You can adapt the amount of data that a client is receiving based on their available bandwidth. We use a custom-built UDP-based protocol. UDP, as you know, is an unreliable protocol, which means that a packet may never arrive, may show up twice, or may arrive out of order. That's totally fine. Our protocol informs us when a packet is dropped so that we can retransmit that dirty state if it makes sense to do so. When that happens, we simply union back in the dirty state from the packet for future retransmission. On some future packet, we can retransmit the fact that Pharah has moved, along with some other things that have potentially occurred on that frame, like Reinhardt popping his shield up. Note that we don't have to transmit the exact old data. Pharah moved in the period in between when the first movement was sent and the later time when the packet loss was when we received a notification of the packet loss. We'll serialize the new movement data instead of the older stale information. Now let's think about somebody who's just connecting to a server or joining an in-progress game. In this case, how do we catch that user up on the state of the world? Well, we maintain on the server a lifetime dirty state set. There's just a lot of dirty state sets, just dirty states everywhere, which is just the accumulation of everything that's ever been dirty ever on that server. You can guess what's going to happen next. Yes, when a new client connects, we set its initial dirty state set to the lifetime dirty set. You can just literally assign that out. Our normal per frame packetization will eventually stream everything for that client out until the new receiver is caught up. All of this is fine and well, but we're here for replays, right? I'm talking about network serialization. Well, you can think of a replay stream as being very similar to a client's network stream, right? It's just a different serialization receiver, which in this case we call a replay snapshot receiver. So one way to build a replay stream not a very good one, we'll refine this in a second, is to dump the entire snapshot of the world, the whole instantaneous world state on every frame. While UDP stream is constrained by the size of a datagram, or MTU, the replay stream isn't. We can dump like tens or hundreds of kilobytes on every single frame until you run out of memory, but that's a whole other conversation. But how do we guarantee that we get a proper full snapshot every time? It's easy. We just act like every hypothetical packet to the replay snapshot receiver is dropped, then recopy the lifetime dirty set to the replay snapshot receiver. This guarantees that every entity is completely dirty on every frame for every snapshot. But as I've already hinted at, this is extremely wasteful. As previously mentioned, our network systems and our network clients have delta encoding. So we can do compression based on previously acknowledged state in order to memorize our network footprint. So we create a second replay receiver, the delta receiver. This receiver never drops our hypothetical packets, so each update contains only what's changed since the previous frame. So literally in that case, you just copy the frame dirty state and it just serializes all that out. So let's put all this together now. At the end of the frame, we've serialized out the new lifetime dirty state set to the replay snapshot target. We've also serialized out the per frame dirty state to the replay delta target. So the question I have immediately after this is, well, where's all that data going? While the normal client receiver streams are going out on network packets, replay data needs to go somewhere else. We maintain two contiguous buffers, one for snapshots and one for deltas. On each frame, we keep an index of the offset and size of both the snapshot and delta for that frame. These contiguous buffers are maintained for the lifetime of a gameplay instance, as designers can request a reel for a play of the game, for example, from like the very first moment of the match. Practically speaking, each buffer consumes about a megabyte of memory per minute. Taking a snapshot every frame would consume considerably more RAM than 1 megabyte a minute, so we lower the snapshot rate to 1 per second. And the astute among you will also be wondering about the update rate for deltas. While our servers run at a full 62.5 hertz client update rate, kill cams and replays running at that rate would have tripled our memory footprint and network transmission for replays, so we lower the resolution there to about 20 hertz. Finally, we're at the point where we can generate the core consumable object for the client. It's what we call a replay reel. When a designer wants to generate a kill cam or play the game, they just request a reel. These reels consist of a single snapshot followed by n incremental deltas, some number of them, however long is necessary for the reel size. To generate the reel, we find the closest snapshot prior to the requested reel start time, then append on deltas until we reach the desired reel end time. The resulting buffer is generated very efficiently. It's just 2 mem copies at that point. We take this buffer, compress it, add some metadata, and then ship it to the client. This same mechanism is used for kill cams, highlights, and plays of the game. They're all supported by this one system. If this is starting to look suspiciously close to how snapshot synchronization works, you're absolutely correct. This is intentional. We're getting the best of both worlds here. We have the flexibility of state-based modeled in order to adapt to bandwidth conditions on clients that are bandwidth limited, and the simplicity of the snapshot synchronization model when it comes to replay reels. All right, so we've got our reel generated and we need to get it to the client. To transfer the reel, we chunk the resulting byte stream into MTU-sized chunks and fling them across the network via a block transfer system we implemented. The block transfer system respects the bandwidth observations we make, flinging chunks only when we detect slack capacity on the wire. Of course, we also benefit from the fact that the player, during this transfer time frame, tends to be dead and staring at the guy who killed him and getting very angry. They tend to be a little preoccupied, and they don't notice potential micro hiccups because we're doing a large block transfer during that time period. So finally, let's talk about what the synchronization API ends up looking like. I've left some parameters out here. The return types tend to be enums rather than ints, but this gives you the basic shape of things. Systems typically implement both the network and replay participant interfaces by thunking into a common serialization and function internally, as there are minor differences between the two APIs. As an example, the network participant API enforces bandwidth restrictions, as we've you've been hearing that a lot now, that the replay participant API doesn't have to worry about. So in many cases, the replay interface will call the internal function with the bandwidth limit to set some crazy limit that should never be hit. As a result of this shared serialization strategy between the network and replays, every bit saved for network replication also saves a bit in the replay stream. These per subject calls are called once per relevant subject for each receiver. So basically, you can imagine going over the entire dirty set and calling this once for each. If all participants indicate that they have no further data to serialize for a subject, it's safe to remove that entity from the receiver's dirty set. These fixed calls provide participants an opportunity to synchronize things that may not be associated with a particular entity. On the network side of the house, this covers things like out-of-band control messages and handshaking and that sort of thing. With an unreliable protocol, each system participating in the network stream needs to receive an ACK or a NACK for each packet it participated in, a NACK being a not acknowledged. We use this previously acknowledged state to send incremental updates with interframe compression. Replay participants, on the other hand, don't have any need for acknowledgement or drop notifications because they don't drop packets, drop memory on the floor unless, well, that would be bad. Instead, we have a pair of callbacks that are invoked immediately before and after replay serialization. As an example of how these functions are used, immediately after we've completed serialization of a replay frame, this is how we ACK all the internal serialization state for the delta receiver, and we NACK everything that happens on the snapshot receiver. This is a simplified API usage example for sending to a network receiver. We make the fixed call for each participant in the receiver. Then we get the dirty subject set and allow each system to participate in serialization for that subject for the receiver. This example glosses over a large number of details that could encompass an entire other talk, which includes dirty state tracking, relevance, prioritization, filtering, our bandwidth modeling, package drops and acknowledgements, and all that other fun stuff that could be in a whole other talk. Beyond the bookending before and after calls, the replay example is identical to the network API example. Looking back at our participant APIs, observant viewers may be questioning why these systems aren't architected based on components rather than entities. In a proper ECS paradigm, one should only be iterating on components at any given point in time. Initially, our synchronization APIs were actually organized by component. As an example, the movement system would simply iterate over all the movers and serialize out whatever it needed. Unfortunately, that paradigm has a few implications associated with it. What happens if we are bandwidth limited? Then serializing by component means that a single system can choke out other systems from being able to serialize that. Beyond that, it drastically increased the likelihood of an entity getting updated across multiple packets. The pragmatists on our team turned away from ECS purity in this case. We tend to shun the non-ECS pure, but in this case it was totally tolerated, and for the sake of a better user experience. All right, that's the core meat of it. Now we get into the fun parts, the challenges and all the lessons learned about some of this stuff. If that was all the how, then this is the when and where, not necessarily the why, because we covered that at the top. First up, when do we transfer a kill cam reel? There are a few fixed points in time for a kill cam. There's the time you die and the time you respawn. The distance between these 2 points is controlled by the respawn timer, which can vary based on the map, the game mode, whether or not you're in overtime, and all kinds of other things that designers can play with. Now, in order for a kill cam to make sense psychologically, you need a little bit of pre-roll ahead of your death. That way you don't just snap in, suddenly sight yourself, gets headshot, and then don't know what the heck happened. But we also don't want a hard cut at the end of the kill cam at the exact moment of your death, the projectile impact. That would also be jarring, and your brain needs a few seconds of context after your death to process things, see your corpse ragdoll, come to terms with the universe. Now this slide's starting to get crowded. Somewhere in between the end of the post-death coda and your respawn time, you need to watch the kill cam, right? That's the whole reason why we actually have this kill cam in the first place. Which leaves that tiny window right there as the period in which we can actually transfer the kill cam. This is about a half second in production right now, and a half second doesn't give you much time to transfer that reel on low bandwidth connection. That provides additional motivation for our team to keep our bandwidth on a diet, right? Again, anything that we do to reduce overall bandwidth envelope ends up reducing our kill cam sizes as well. In practice, being disciplined about this has led to a very reliable kill cam experience, even on low bandwidth and lossy connections. There's another option here, which we considered briefly. Rather than making a single large bulk transfer, we could conceivably transfer the pre-death content immediately at the time of death, then stream deltas down incrementally after the fact. This approach comes with some engineering trade-offs, however. Our total bandwidth usage would likely increase, as we wouldn't be able to do a single compression pass on the entire reel. There's also some control mechanisms in there where even if you've received the first block of the kill cam, you wouldn't necessarily want to start it, because if you don't necessarily have the data that's at the end of it, you might stall out, which then leads to stuttering in your kill cam, which nobody wants to see. All surmountable. We haven't needed to do it yet, but it's an option on the table if we ever have to do it. Oh, I think this one's my favorite.
Heroes never die.
Nice save.
Yeah. Interruptible kill cams. Resurrection is a problem. So we've transported a reel to the client, and it's going to play back. But we can't completely clear the live world state because the kill can be canceled or interrupted at any given point. We can't stop the network stream because scripts that are on the live game are potentially controlling UI and stuff that gets triggered in order to signal the fact that you're getting resurrected. We also aren't using a snapshot synchronization model, so we can't just easily keep all the world state around on the client. We don't have a save game system. We never implemented that. So playback has to still be immediately interruptible. So what do you do? Well, Overwatch's gameplay layer sits on the previously mentioned ECS architecture. I had a thought. Why not just provide a separate execution domain, or in Overwatch terminology, an entity admin, for the replay? You've got two disjoint ECS domains. We can completely isolate the replay execution from the live game. Asking around, I surveyed engineers and leads in our tech direction. I was assured absolutely that for the kind of game we were making, CPU resources were never going to be our primary constraint. What could possibly go wrong here? I mean, we'll never be sim-bound. Seemed like a totally sane task. And for the most part, it was. This was a great opportunity for us to clean up some design patterns internally that relied on global and static information. If you have completely disjoint execution domains, all of your execution parameters need to be under those domains wholly. So it was great. It was a nice code cleanup task. After a few weeks, we had everything properly isolated, and we had one entity domain for the live game and one for replays. In this model, the live gameplay stream is coming off the network, and it's going right into the live entity admin. We get a block transfer on the replay, and that goes right into the replay entity admin. When you're in a kill cam, you're actually simultaneously processing both streams at the same time. In our simple kill cam here, I'm going to show there's going to be a black fade that occurs on entry to kill cam that represents a transition point where we stop rendering the live game and then transition to a rendering the scene of the replay domain. And at the end of the reel, we actually transfer back. Transfers occurring, somewhere around there. Transition, we're now in a completely different world. And back. Overall, the domain experiment was quite successful, perhaps overly so. We couldn't stop at just 2 execution domains. Why not 4? It was not a completely pain-free process, however. I mean, the transitioning between domains required us to invent a mechanism to coordinate the communication between the domains. Much of this inter-domain wrangling is scripted behavior, relying now on this critically necessary global entity admin that coordinates where we're going at any given point in time. So what about all the costs associated with this extra simulation load? Well, we ended up being sim-bound, particularly on consoles and lower-end PC machines. While the multi-domain model contributed to this extra load, it was by no means the sole system that broke that processing budget. And with the replay system in place, we were able to use replay files to iterate and experiment with optimizations, which then was overall a performance win. Our replay file support directly contributed to our ability to ship a 60 FPS game on consoles and really helped us hit our performance goals on low-end PC hardware. To paraphrase The Simpsons, replays, the cause of and solutions to your performance problems. On to polish. I said the last one was my favorite. I think this one actually might be my favorite. So first up, turrets. Turret kills were a particularly thorny problem for us. The player who placed the turret, and thus got kill credit, could be halfway across the map while the turret goes on some kind of murder spree. Even worse is if the responsible player is deceased. This is a sample play of the game from Torbjorn, whose turret was doing all the work. Now let's count the elimination messages, shall we?
Play of the game.
One, 2, 3. That's, yeah. It's really infectious laughing. This was from, I think, our beta at the time. We hadn't quite fixed this particular bug. We don't, give play of the game to dead people anymore. That kind of handles that case. So it should be pretty clear that a kill cam from Torbjorn's perspective really only makes sense if Torbjorn and not his turret is doing the work. So how did we handle this? Well, we scripted the turret kill cams. We initially adjusted the kill cam for a turret to show the turret's point of view. Unfortunately, there's a reality of turrets. They're controlled by AI and not people. They don't have a first-person rig going around going pew, pew, pew. And more importantly, the turret AI doesn't necessarily aim in a fashion that makes sense to players. We resolved this issue by creating a custom camera view based on an animated bone on the turret. From that bone position, we recast to a halo of points backwards a bit in order to find a stable viewing angle. This was particularly important for Symmetra's turrets, which are tiny and can be placed on the ceiling or in the corner or up against the wall. It was important for us to have both the turret and the victim in frame to sell the moment of the kill. This video shows an example of the turret cam. Note that on the player's death, we ragdoll their corpse, point the camera at the killer. Once in the kill cam, the camera tracks the player around as they round the corner, and you'll see the turret smiting the player into oblivion. As a bonus, I've included another run here with the camera placement debug pane up. There'll be green points, which are the kind of camera points that we want to have in frame in order to have the turret in frame while we're going through the kill cam. One final note about this video, it also shows how our gameplay debugging functionality continues to work from within the context of a replay. So if I see a bug here, I can actually kind of scrub through the scripting system's debugging facilities.
A turret lies in our way.
This is the debug pane up.
A turret lies before us. It is quite
You'll note there's some interpolation on the desired camera position and other things I kind of glossed over, but that's the nuts and bolts of it. Here's an example where the turret camera isn't quite working as expected even in the shipping version. You'll see the camera on death point at the killer again, but in this case the camera positioning and the kill cam doesn't quite manage to get the sentry turret in frame. Yeah, that turret should be right below there. If you maybe I'll play that one more time. It's these ridges on the ceiling that are preventing my camera placement from working. Sad times. All right, beyond turrets, we ended up implementing custom scripting for quite a few other cases of ambiguous kill cams. When you fall off an edge, we detach the camera and follow your ragdoll into the icy abyss of the river in Volskaya here. If someone knocks you into the ice, however, we intelligently roll a kill cam from their perspective instead. I don't want to live. Totally expected. This was my own fault. I did this to me. Reconsider my life choices. All right. And I really hate lightning. Hanzo's Dragon Strike created a similar problem to turrets. He can launch his ultimate from the spawn room if he wants, and then the dragon can fly all the way across the map and end up killing you while he's kind of sitting there in the spawn room. Showing a kill cam from the killer's behavior in this case just isn't going to make sense. Instead, we put you into a third-person camera, tracking the crawl of the dragon throughout the map until it takes you out. We actually have quite a few other custom kill cams I don't have enough time to cover in here, but this is kind of the majority of the common cases. Each of these customized experiences incrementally polish the death and kill cam experience, reducing the confusion that can spring up around an unexpected early demise. All right, interpolation hinting. From the server's perspective, shooters are always taking actions in the past. Without any additional hinting, the client replaying a kill cam would see shots aiming behind their targets. That's no good, that leads to forum posts. To fix this, we record an interpolation delay hint per player into the replay stream, then integrate that into the interpolation delay buffer during client and real playback. This ensures that the kill cam shows an accurate server-side representation of the shooter's actions. Here I have 2 kill cams I'm going to be playing back-to-back via our internal replay file support with a little bit of time scaling applied. Look carefully at where Soldier 76 is positioned when the recoil kicks in for the shot. Note that in Overwatch, we don't delay weapon volley information. As soon as you have a weapon volley come through, we'll actually trigger the effects and everything else associated with it. That's the boom of the shot trail, and all that. And that, as a result of that, during a replay, because it's at a lower granularity than our client frame rate, you'll see that a little bit off. But the recoil that occurs on shots is controlled by a script and is frame accurate. So the client kicked up right where the actual head was under the crosshair, which is perfect, which is what we wanted. All right, this is the same thing without the interpolation happening. What? No. I'm going to the forum. All right, fast forwarding. Given that we're only taking 1 snapshot per second, and our post-death coda period is 2 seconds, what happens if the nearest snapshot before the desired real start is nearly the full second prior to it? That snapshot is going to truncate the post-death coda period down to a single second, which really isn't enough time for you to contemplate the universe, as I was mentioning. To solve this problem, we adjusted our real playback to fast forward through frames up until the actual desired real start time. It was a small but important change that ensured a consistent kill cam experience. No video here. The server time step. If the server is overloaded, it may fall behind a frame or two and then catch up. When that happens, the frame it is simulating might not fit into its planned time step. When the client then goes back to play the replay, it will have fewer frames than it expected for the length of the reel, and it will end abruptly at the end. The fix for this was fairly straightforward in hindsight and landed around the time we began experimenting with the higher client update rates in the beta. We now record both the expected and actual server time in the reel, which allows the client to play back the reel within the expected time window. Targeted message proxying. Most of our game messages are targeted at a single player. The replay needed some, but not all of those messages in the stream. Spectating has a similar issue, by the way, where not all messages directed to a specific client should be dispatched to a spectator. To accommodate this, we now annotate each gameplay message to specify whether or not it should be included in the replay stream or spectating streams. We then proxy those messages to those receivers as appropriate. During real playback on the client, we filter the messages that are not targeted to the currently viewed subject. Without this bit of polish, reels were missing damage notifications, hit acknowledgements, various UI toasts, and some voice lines that really helped sell the experience. Future work. All right, improving the delta capture rate. As mentioned in the previous slide, our delta refresh rate now is 20-ish hertz, which is a compromise between our desire for accuracy on the wire, accuracy and on-the-wire transfer sizes. Top-tier players can and do land shots while making very rapid rotations that our current capture rate really doesn't accurately represent. One option here is to add some additional orientation hinting to the replay stream, similar to our interpolation hinting. Another is just to increase the delta capture rate to match the current command frame and client update rate. Both of those options will require a potentially large and expensive increase in bandwidth and storage sizes. Player movement already accounts for almost half of our bit stream sizes. For an idea of why this is a problem, I took one of our high-skilled players on the floor. He's a very nice guy who was very willing to headshot me over and over again until we got the video. He's got some great twitch shooting skills. You can see that the reticle is going to pass through the point of the headshot, but without finer grained delta updates, we're interpolating over a pretty broad 50 millisecond range here. This is real time. Yeah, he's that good. And in slow-mo, I have so much to live for. Boom. Note that the reticle actually does pass through where the headshot was, but yeah. You can see why the increased fidelity would be important. Replay file improvements, fast forward, rewind, and scrub. So our current replay files only have one snapshot at the beginning. So they act kind of like a normal like input-based replay mechanism where you only have the option of starting at the beginning and then rolling forward. As a result, scrubbing is impossible. And fast forward is implemented by starting at the beginning and fast forwarding where you want. And we implemented rewind, much to the chagrin of people who actually try to use rewind, because all it does is start at the beginning and then fast forward to like 30 seconds prior to where you wanted to go. It's gotten us by internally, but that's not going to cut it for a player-facing feature that might be released. This is a pretty straightforward fix. You just take more snapshots. I think at our current snapshot size, we could probably include snapshots at a 10-second or so granularity in replay files. And without compromising too much on the file sizes, that'll let us seek and fast forward, at least within that, up to a 10-second kind of snapping window. If we add those additional snapshots to the replay file stream, a scalable spectate feature pretty much falls out very, very neatly out of that. You can just imagine a proxy or server that's receiving the replay snapshot and delta streams, separate from the instance server where the active gameplay is occurring. As more players want to spectate a live match, like in a tournament, we'll be able to simply send down the snapshot to those players and then start streaming the deltas to them, all on an isolated server well away from the live gameplay, so we're not overloading a particular server that's very, very important potentially. Add a touch of buffering, a little bit of UI, and voila, scalable spectating. Pretty sweet, right? I thought I was really clever when I was designing this into our original feature set. It turns out, though, that I'm actually not clever. This idea is completely and totally unoriginal. It's the exact same model that Valve uses for their scalable spectating, which I think they call Source TV. I'm guessing Dota 2's in-game spectating relies on this infrastructure. But, you know, at least great minds think alike, right? Replays for players. So finally, I would be remiss if I didn't talk briefly about what it might take to put replays out as a player-facing feature. Players want replays, and we want happy players. There's just some logistics that are involved here. Our biggest obstacle, honestly, is finding a way to retain all of the replay data we'd like. At current rates, our estimate is roughly 200 terabytes a week of storage churn on keeping compressed replays. Unfortunately, compressing takes CPU, and CPU time is the thing we're actually most heavily constrained on. Beyond that, retaining 200 terabytes a week is not something you want to accumulate forever. We're investigating how to balance these storage requirements with our retention needs in order to make this feature real. We want a period that allows players a reasonable amount of time to download replay onto their local machine. We've also, I might note, briefly considered allowing players to download a replay file at the end of the match, but that would have just added a bunch of network transfer costs onto already the most loaded servers that we have, so that was also kind of a no-go. And if we're talking about retention, questions about patching and serialization compatibility pretty much immediately follow on to it. Our network and replay streams both depend on asset definitions for deserialization support. Patching anything involved with that stream can make the replay file incompatible. For reference, I think the rough estimate was between our launch in May of 2016 and December of 2016, we patched 22 times. That would have been 22 potential invalidations of replay files, which I don't think anybody really wants. All of this implies that we need to have a client potentially support loading asset definitions associated with the previous patch in order to be able to play the replay back. That means potentially streaming that content down if they don't have it on disk, some form of asset overlaying to be able to load the older versions of the assets to the newer versions, on-demand streaming from our CDNs. There's going to be a progress bar. You can kind of see the requirements here stacking up. We're actively working on hammering out what this feature might look like, but this hopefully gives you an idea of some of the obstacles and barriers that we're trying to overcome. Recap. With that, do we reach the end? So, replays are just cool. This video demonstrates some of our cinematic gameplay camera support. Yeah, bullet time. So you can imagine combining this functionality with some time scaling, pausing, you get this matrix-like bullet cam support. This functionality was heavily used in some of our first gameplay trailers. So I just unpaused there, move the camera around a bit, and I'm like, oh, well, okay, cool. Oh, yeah, we can get a better view here. Let's come on over here. So what did we learn? Design your network synchronization model with replays in mind. Disjoint execution domains for us provided great flexibility and isolation. Network bandwidth optimizations in this model double as replay file sizes, so if you can save a bit, please save a bit. And the community really loves showcasing highlights and play of the game. It's been really amazing seeing the Reddit community and other communities online kind of gathering around these features. Replay file support, if you don't have replay files in your development, I'm sad for you. You should lobby your engineers, or if you're an engineer, you should really, really try to do this. It's really great for being able to debug things. It's also really great to have replay files around for nearly deterministic performance replication. You can iterate on something, potentially optimize, and get your game really working on all the hardware that you want to support. More domains meant more load. That was definitely a somewhat unexpected headache, and it really required a lot of effort on our engine team to kind of help out and smooth transitions that are going on in between domains. Like, we did an entire pass on making sure our scene update basically had a lo-fi mode that happens to whatever scene is in the background in order to reduce their CPU footprint. Bespoke serialization can be expensive on the server. This is actually, it's not like anywhere near the top line item for dealing with serialization, but the more bespoke streams that you're creating, the more important it is for those things to be optimized. So it's definitely something that can bite you if you're taking this model into heart. And then the last thing, you'll note that the serialization APIs that I have, those are the ones very close to the ones we actually have in production. They're so similar that at this point I don't know why I didn't just bother merging them in. So I think if you pitch a common synchronization pattern earlier, and it's going to lead to cleaner APIs. And that is it. Now we're open to questions. Looks like we've got, what, 9-ish minutes. So.
Hey. So you have a lot of breakables and dynamic objects in the game. How much of that do you take a snapshot of? Would you take a snapshot of everything? And how many of the pieces do you take snapshots of if you do that?
That's a great question. So breakables are actually kind of funny. Initially at launch, every breakable was an entity. So it went through the full entity serialization pipeline. And then at one point, I think it was about 3 months ago where we actually shipped this change under the hood, I flipped the table and I was like, that's way too many bits for something that isn't changing very commonly. That's bloating out our snapshot sizes. Like, it goes from not broken to broken. That is 1 bit. All you need is 1 bit. So we implemented a pattern where we instead bake out, based on the map data, it's just a breakable bitmap. So now that bitmap is all that's synchronized, and that thing is like 200 bytes in total on the snapshot, and then every time something changes, I think it's like, for a 4-bit range, it's like 7 or 8 bits to replicate whatever's going on there. It's much more optimized that way.
Thank you.
Yeah.
Hey, so StarCraft 2 had a replay system. Did you guys try to make use of that? Were there any pitfalls there?
So StarCraft 2 is based on deterministic lockstep simulation, so their replay file support is really based around that start from the beginning and then roll forward approach. They also implemented save file support. Because we're not actually doing deterministic lockstep simulation, and mostly for the reasons that I mentioned at the beginning of this talk, where it has some definite drawbacks on the more players that you're involved on. We definitely talked to the StarCraft 2 team, and we arrived on the solution that we had as a result of some of the guidance from them.
Thank you.
Mm-hmm.
You experimented with component-wise serialization. Was there the idea of serializing them at different temporal resolutions? For example, you mentioned the rotation, where you could have benefited from that.
So potentially, I mean, the temporal aspect of things is kind of an interesting one. Right now, because we've been very, very aggressive about our bandwidth usage, we haven't necessarily had things fall out or spill out of a packet. Generally, everything that happens on one individual server frame will fit into one packet. And because of that, we haven't needed to do a thing where we're potentially doing area of interest headaches or anything else along those lines where we start striding. It's totally possible. It's just one of those things where I have a whole series of things in my back pocket that I'll probably continue to do if we start adding a lot more dynamic objects or other things that make that necessary.
Thank you.
So this is a highly specific question, but I'm a tryhard and I switch my reticle around, and I noticed that in a replay, it won't pick up your local player settings for whatever player is shooting at you. And I sort of assumed it's just like ignoring your settings locally, but I was wondering like why that only happens to apply for replay, because it seems like it should be able to pick it up.
That's probably, I mean, from my point of view, there's a design question there, which is which reticle should you see when you're seeing a kill cam?
Yeah, that was the other thing. I was wondering like if you send that for some reason.
Yeah, like from my point of view, I would ask a designer, if the designer wants the person to see the remote player's reticle, then we would definitely want to include that in the replay stream so that we could actually provide that kind of nice fine-tunement. The fact that we're not showing that in the replay scene is just an artifact of the fact that it's an execution domain that doesn't have your personalization settings applied. So
that's what I figured.
Yeah.
Thanks.
Hello. So for physics-based simulation like ragdolls or Zenyatta balls dropping down or something like that, so what do you do? Do you let the physics engine re-simulate the same animation, or do you do it frame by frame?
So we have a split between client and server authoritative simulation domains for physics. So things like the Zenyatta balls, hair, and ragdolls are actually only client authoritative right now. We don't do what Halo does, where we actually try to synchronize the ragdolls. So if you notice, you can shoot right through ragdolls. That's not an issue in our engine. And that's mostly for optimization purposes. It would take more bandwidth. It's totally doable, but then that gets into the, well, now I need my AOI and my striding on individual objects in order to handle that right now.
Okay, thank you.
All right. Well, thank you all. If you guys have more questions, I'll probably be milling about over here, so thank you again.